Hi, I'm Luca Luigi, and in this talk I will present you the work Plugin Self-Supervised Monocular Depth into Unsupervised Domain Adaptation for Semantic Segmentation, done together with Adriano Cardace, Pierluigi Zama Ramirez, Samuele Salti, and Luigi Di Stefano. Our work addresses the setting of unsupervised domain adaptation for semantic segmentation, where we are given with a source domain composed of synthetic images paired with accurate semantic labels that can be used to train a deep learning model for the task of semantic segmentation. Our final goal, though, is to deploy the trained segmentation model on a target domain, usually composed of images from the real world, where semantic annotations are not available. However, the model trained only on the source domain will produce bad results when tested on the target domain because of the so-called domain shift. To overcome this issue, many UDA methods have been proposed in the last years, with impressive results. The overall idea behind our proposal can be summarized in 3 points. First, a molecular depth estimation network makes predictions based on the appearance of objects in the images. This suggests that the network has to understand implicitly the semantic of the scene. Nowadays, effective self-supervised procedures allow for training a molecular depth estimation network without the need of ground truth labels. Thus, we propose to infer semantics from depth, exploiting the possibility to obtain depth proxy labels also for the target domain with self-supervised monocular depth estimation algorithms. We observed that semantic prediction obtained from depth tend to be smoother and more accurate on objects with large and regular shapes, while other UDA methods excel on the fine-grained details of the scene. Thus, we decided to design our method as a plugin that can be plugged seamlessly in any UDA method to boost its performances. Here's an overview of our method, which is mainly composed of 2 steps. RGB images are first processed by 2 different segmentation engines to produce complementary predictions that are then combined by a weighted sum which accounts for the relative strengths of the 2 engines. After that, predictions from the previous step are used to synthesize augmented samples by mixing portions of different images according to depth and semantics. The augmented samples are used to train a final model so as to distill the whole pipeline into a single network. Let's dive into some detail. Based on the intuition that a segmentation network can benefit from information on the geometry of the scene, we design a semantic engine dubbed Semantics from Depth. More specifically, we exploit a self-supervised monocular depth estimation method to obtain depth proxy labels for both the source and the target domains. Then, on the source domain, we train a network as a transfer function between the deep features extracted for depth and the ones extracted for semantics. The transfer function, even if learned on the source domain, can be used also on the target domain to infer semantic from depth. After that, we merge the predictions from our semantics from depth and from any UDA method of choice, with weights computed according to the frequency of classes at the pixel level in the source domain. In the last part of our pipeline, dubbed depth-based self-training, we exploit semantic prediction from the previous step and depth proxy labels to build a large and varied dataset of plausible samples that we deploy in the final self-training procedure. The image on the right shows how the new samples are generated. The rightmost column is synthesized by copying pixels from the left column into the central one. Pixels are chosen according to their semantic class, presented in the second row, and stacked according to their depths, reported in the third row. We evaluate our framework in 2 popular benchmarks, where the source domain is either GTA5 or Cynthia and the target domain is Cityscapes. Quantitative results show that our method can be seen as a plugin capable of boosting the performances of all UDA methods, even the most recent ones. Qualitative results confirm that our approach can exploit effectively geometry information of the scene to improve the prediction of any UDA method, especially on objects with large and regular shapes, like roads and sidewalks. Such improvements can be appreciated on both benchmarks. Thank you for listening to this talk. Feel free to check out our paper and the code on GitHub using the QR codes provided here.